Have you ever used an epoxy glue? Epoxy glues usually come with a double syringe containing two different solutions. You push down the syringe, out comes an equal mixture of each of your two solutions. You mix it up, apply it to your desired target surface, and after the curing time, you have your hardened glue there, sticking your surfaces together. The epoxy glue relies on a reaction of our epoxide organic functional group. Epoxides are unique derivatives of ethers. So an ether, of course, is a functional group with an oxygen bonded between two carbons. Our epoxide still has that oxygen bonded between two carbons, but those carbons are also linked to each other to create a little three-membered ring. Now, this epoxide will share a lot of similarities with ethers due to that similarity in structure there, but because of this small ring, within a three-membered ring, of course, we only have 60-degree angles between each of our bonds. Right? So our bonds are squished together significantly more than they would like. Right? Normally we want a 109.5 degree angle in our typical sp3 hybridized carbon. So we're squishing those bonds closer together. That means we have a lot of electron repulsion between these bonds, and our ring system is less stable than it would otherwise be. Right? So we've got a lot of steric strain within our ring, and that's then going to allow some unique reactions as our ring is going to be more likely to react when we can break open that ring to form a new compound. So epoxides are significantly more reactive than their close cousins of the ethers. Let's first take a quick look at naming our epoxides. So our epoxides will use a slightly different naming system compared to our ethers because, of course, here we have to deal with that cyclic system that we didn't have in our normal ether. We commonly see three different ways of naming our epoxides. The first possibility is based off of naming our three-atom system here as an oxyrane. So oxyrane is another name for our basic epoxide functional group. So if we have a slightly larger epoxide, such as this one here, so we have now our oxyrane with a methyl group coming off of it. So this would be a methyl oxyrane. So our first possibility then is naming it as an alkyl oxyrane, naming just it as our epoxide and then naming whatever is branched off of that. The second possibility is naming that epoxide as a branch coming off of our alkane chain. So this would be naming it as an epoxy alkane. Here we would need two numbers in order to indicate the two carbons that are attached to that epoxy group in the ring. So here we have our three carbons here. So this would be propane. And in this case we have our 1,2-epoxy propane. So it's relatively simple, very similar to the substituted naming of all of our other functional groups. Just finding those two carbons on your parent chain that are bonded and indicating that as an epoxy group. So that's perhaps the easiest method of naming our epoxides. The final naming system that we commonly see is naming it as an alkaline oxide. So this naming system kind of suggests the presence of a double bond. Of course, the reason for this is because our epoxides are going to be synthesized from alkene double bonds. So it's actually formed by oxidizing, adding our oxygen to an alkene, and so that's where kind of that alkaline oxide name comes from. So in this case, we have our three carbons here, so this would be our propylene oxide, based on the number of carbons that are in our chain, including that epoxide. Of these three different naming systems, so the epoxy alkene system is probably the easiest to use just because it's very similar to our normal substitutive nomenclature naming system. The alkaline oxide method, though, is commonly used in industrial applications. So if you look at any epoxy glue that you have, it probably lists the epoxide ingredient as some form of alkaline oxide. Now, how do we make these epoxide compounds? There are two different common ways to synthesize our epoxides. The first involves an alkene addition reaction that we looked at last semester. So we can start from any alkene, and then if we add a peroxy acid, so peroxy acid, we have our carboxylic acid functional group with an additional oxygen-oxygen bond there. So our peroxy acid would look something like this. This peroxy acid breaks off one of those oxygens and adds it on to our double bond. So we get our epoxide with the same carbon structure as our original alkene. And of course we also get our carboxylic acid byproduct from the peroxy acid as well. So I won't really go into any more detail on this reaction. We talked about that some when we looked at alkene addition reactions. The second possibility would be to use an intramolecular Sn2 reaction. So in this case we need to start off with a compound that contains an alcohol functional group and an adjacent halogen. So we call this a vicinal halohydrin. Vicinal, of course, referring to our functional groups on adjacent carbons, our halogen, and our hydroxy group here. And then what we're going to do is we're going to add basic conditions. So if we add a base here, so our base is going to allow us to deprotonate our oxygen here to create a alkoxide. And then we can do our intramolecular Sn2, where this will attack and kick off our halogen, and we create our epoxide. So we end up with our oxygen bonded to both of our two carbons here. Our halogen leaving group has broken off, and of course we have our desired epoxide product sharing the same carbon structure as our original vicinal halohydrin. Now notice here, of course, that one of the easy ways to make a vicinal halohydrin is actually from an alkene. Right? If we take an alkene and we add our halogen and water in a cohalogenation reaction, this would actually produce our vicinal halohydrin for us. So generally, regardless of which of the two synthesis methods we use, we're usually going to start from an alkene. Once we form our epoxide, the most common reaction that we see with our epoxides is a nucleophilic substitution reaction where we break open that epoxide ring. So within our epoxide here, we have our nucleophilic oxygen, of course, due to the high electronegativity of our oxygen. So that's pulling electron density away from both of our carbons here. So we have electrophilic sites. And we further have this incentive of once we attack, we can break one of these bonds to free that strain within our ring system. So we can react with a variety of different nucleophiles. I'll represent that as just our generic Nu representing any nucleophile. This would attack our electrophilic carbon. We break our ring at the same time, and we end up then producing our ring opening product, where we have our oxygen bonded to one ring, or one side of our original epoxide ring anyways, and we have our new nucleophile added on the other side. Since this is a substitution reaction, our nucleophile is always going to end up anti with respect to our oxygen, right? So it's an anti-addition reaction, and of course, this initial alkoxide is usually going to get protonated to form an alcohol product. So let's say we react our propylene oxide with a methoxide reagent here, acting as our nucleophile with a methanol solvent. So again, this is going to be our nucleophile with a negative charge here. Of course, our sodium is just our counter ion. And we're going to be attacking our carbons here that are electrophilic, using that ring opening to help to push our reaction forward. Now you'll notice here, of course, we have two unique sites that we could attack, right? The carbon on the right has less carbons attached than the carbon on the left. Since this is a Sn2 reaction, essentially, we're going to attack that less substitute position where there's less crowding. So we attack the less crowded position. Our basic nucleophile attacks the less substitute position, following typical Sn2 preferences. Once we complete that attack, now we're going to have our alkoxide on one side, and of course our newly bonded nucleophile alkoxide on the other. And then we'll react with our solvent to protonate our alkoxide here. And so our final product then, again, as we saw before, is going to be our alcohol with our new nucleophile added on at the less substitute position of our original epoxide. Now this rule of substituting at the less substitute position does not always apply. So if we have the same reaction under acidic conditions, in this case our oxygen is actually going to react first with our acid. So we take the hydronium ion that's created by our acid, in this case sulfuric acid, and we're going to first protonate our oxygen here to create our protonated epoxy ring. So now we have our oxygen here with a positive charge and our two carbons here as well. And our oxygen is actually going to share that positive charge with each of our carbons here. So we get extra positive charge here at our two adjacent carbons. So our partial positive charges become even larger as we're sharing some of that positive charge of our oxygen. And so when we bring in our nucleophile now, so our nucleophile is going to be our alcohol in this case, our nucleophile is going to attack the location that has the larger positive charge. Well, as we know with our carbocations and our carbons, right, the positive charge is going to be most stable at the most substitute position. So this position will have a larger positive charge, and under acidic conditions it's actually going to be more favorable to attack that position. So this will get attacked, we'll break open our ring, and we'll actually be substituting now at the more substitute position. And then of course to get our final product we can bring in the water that we created in the first step and deprotonate this alcohol here in order to create our product. So we have our nucleophile added on here at the more substitute position, and of course the alcohol that formed from our epoxide ring is right here at the less substitute position of our original epoxide. So overall then, if we're reacting under acidic conditions, we prefer the more substitute position. And if we're reacting under basic conditions, then we attack the less substitute position. So we can actually vary what product is formed based on just changing whether we have an acid or a base catalyst, right? Previously we had the base, the alkoxide form of our methanol. Here we have just methanol with an acid catalyst. In both cases we're getting the same overall product, just with a different substitution site of our nucleophile. And again, I'm using oxygen-based nucleophiles here, but this nucleophile could be any of the different nucleophiles that we've looked at, right? It could be an organometallic nucleophile, it could be a sulfur-based nucleophile, any kind of nucleophile, as long as it's nucleophilic enough to attack our epoxide, as long as we have the acid or base catalyst here to help with that reaction, we can still break open our ring and form that new product. To close here, I want to show you what the actual reaction of our epoxy glue looks like. Now the details of this reaction will vary depending on what epoxy glue you buy. Each manufacturer, of course, has their own proprietary mixture that they think makes the best possible properties for that glue. But in general, what we're going to do is our two tubes that we have in that dual syringe will have two different key compounds. In tube 1, we'll have some form of a diol with two different alcohols linked together. Again, of course, the exact carbon structure of this diol will vary depending on what epoxy glue you purchase. And then in our second tube, we'll have the epoxide. One of the common things to do is have our epoxide linked together with another halogen near that epoxide. So you've got some compound like this, your epoxide, and a halogen on the same compound. Now with our epoxy glue, we're going to be taking these two compounds and mixing them together in equal proportions. And we also generally include some base in our mixtures here as well. So we have a base present, such as sodium hydroxide, we have a nucleophile, and we have our epoxide ring. So under basic conditions, we can take our nucleophile and attack the left substitute position of that epoxide ring. This will break open our ring, and we'll get a product that looks something like this. We have our new oxygen now linked to the ring, or what was the ring. The ring opens up, our oxygen ends up on the more substitute carbon, and we've got our chlorine over here. Now notice our oxygen here and our chlorine now make a vicinal halohydrin. So we can actually take this and react again. So this guy is going to attack and we'll kick off our chlorine. I would need to rotate my chlorine around, of course, to have it, so I'm attacking from the back side. And that will now produce a new epoxide on the end of my molecule here. Now, of course, we can link this end on to another unit. So I can bring in another epoxide unit with my chlorine over here. Again, I have basic conditions, so I can attack, open this ring, and that will now react on to form. So my diol now will be linked to two separate epoxides. So the second epoxide now, we've got our new alcohol forming at the last substitute position, and our chlorine over here. And we can again attack in an intramolecular reaction and remake our epoxide ring. So what you see here, right, is that our diol is able to cross-link between two different epoxides. Right? So we link two of our epoxide units together, and we then even regenerate our epoxide. So this can actually go on to react with more of our diol. Right? And we can actually keep linking these together and creating our polymer. Right? Once we've gotten to this point, right, we're actually back here with another epoxide. We can bring in another diol unit, and we can react again, and we can continue this process, right? So this can just keep on going for as many cycles as we want in order to create that polymer. So since our diol or our epoxide basically will react and then recreate the epoxide, so it can react again. Our diol, of course, can always react on two sides with two different epoxides. And so this chain reaction can just keep linking these individual units together. We'll alternate between a diol and an epoxide, diol, epoxide, with these two different monomers repeating again and again in our polymer. Right? So I won't go any further, but of course you could continue to repeat this for theoretically as many different units as you wanted. That actual polymer that's created then is what will then act as our glue and hold our specific substances together. Right? So it's actually that new polymer that forms then, it actually creates a physical polymer that holds your two things together that you're trying to glue with that epoxy glue. So what we see here with our epoxides is that even though it has a lot of similarities to our ether structure, just by linking it into this ring system, we're able to create some new possibilities for our reactions. Right, so now with that ring we have, it's very favorable to break that open, and so we encourage this nucleophilic attack. That allows us to make very useful things like this epoxy glue. This reaction is even used in the body as well. So the synthesis of cholesterol actually uses an epoxide that then gets attacked in order to form our cholesterol molecule. So it has a wide range of uses both in the organic lab as well as in biochemistry.